Good evening, everyone. So this is our lecture number 3 for motion along a straight line. In the last lecture, we discussed about some problems related to motion along a straight line. And in this lecture, we'll be starting with one of the problems related to average velocity, right? And then we'll be further discussing about the different aspects of this motion along a straight line, right? Let's try to solve this problem on the screen here. The problem is that if velocity of a particle is given by that's v is equal to 2t square. It's as a function of time, 2t square plus 3t plus 1, where t is time. And we are asked to find the average velocity between the interval 0 and 2 seconds, right? So between time t equal to 0 and t equal to 2 seconds, we have to calculate the average velocity. And velocity has been given as a function of time. We know that when we studied about the studied basic mathematical tools, we studied there in case of applications of the integral. One of the important application we studied there was to calculate the average of any physical quantity, right? So what we studied there in case of basic mathematical tools, that suppose that if we have any physical quantity f of x and we want to find average of this physical quantity, the average of this physical quantity is nothing, it's f of x dx, integral of f of x dx. Let's suppose it's between the interval x1 and x2. So it will be, limit will be from x1 to x2 over integral of dx with limits x1 to x2. So this is how we can find the average of any function, right? F of x. And similarly, here we have been given a velocity as a function of time. So we can find the velocity, average of velocity, like, so it will be nothing, integral of v dt, right? Over integral of dt with the limits. Limit is between 0 and 2 seconds, because between 0 and 2 seconds we have to find the average velocity. So it will be 0 to 2 and 0 to 2 here, right? So our average velocity will be nothing, that will be equal to integral of v is given as 2t square plus 3t plus 1. So 2t square plus 3t plus 1 dt over integral of dt. The limits here 0 to 2 and also here limits 0 to 2, right? So integral of dt with respect to t will be t, and the limit is from 0 to 2. So it will be nothing. It will be 1 over 2 integral of dt square, 2t square plus 3t plus 1 dt with the limits 0 to 2, right? The limits will be from 0 to 2 seconds, right? So average velocity will be nothing. It will be 1 over 2. The integration of t square is nothing. It's t cube over 3, right? So we'll be left with 2t cube over 3, 2t cube over 3 with the limits 0 to 2, and the integration of 3t will be 3t square over 2 with the limits 0 to 2, and the integration of 1 will be nothing. It will be t with the limits 0 to 2, right? So from here we can substitute the value of the upper limit. So it will be half of 2t cube. It will be 2 cube is 8, and multiplied by 2 it will be 16 over 3, and 3t square over 2 it will be 12 over 2, that's 6 plus 2, right? So from here we'll be left with 8 over 3 plus 3 plus 1. So it's nothing. It will be 12 plus 8, that's 20. That's 20 over 3 meter per second. So this comes out to be the average velocity between the time interval 0 and 2 seconds, right? So this is how we calculate the average velocity using the integration method of integration. We can also calculate the average velocity using the concept of the total displacement over total time. And this is one more way to calculate the average velocity using the concept of integrations, right? So that's what's it. Now we will be further discussing about some of the definitions related to motion along a straight line, right? Some of very important definitions, correct? So one of the definition we study is uniform velocity, right? So uniform velocity is nothing. We can say constant velocity, right? So velocity is uniform velocity is nothing. It's just the constant velocity, right? By constant velocity, we mean that the direction as well as the magnitude of the motion of that particle is not changing. I mean to say that the speed of that particle is also not changing and the direction is constant. So both the magnitude as well as direction of this physical quantity is constant. So it means that constant magnitude and fixed direction, right? Neither the magnitude of the velocity is changing means neither the speed is changing nor the direction of the velocity is changing. We can say that the velocity is uniform, right? And the velocity will be non-uniform in the case if any one of these changes, either the direction change or the magnitude change, or both can change direction as well as magnitude of the velocity, right? We can call that as non-uniform velocity, right? That will be non-uniform velocity. So it will be called as non-uniform velocity. So non-uniform velocity is nothing. Suppose that either magnitude of velocity change or direction of V change or both change. So non-uniform velocity is nothing. Magnitude of velocity is changing, right? Direction of velocity is changing, or both can change simultaneously, right? So we can say that let's suppose that we have a circular motion, right? Let's suppose that for this example, let's suppose that we have a circular motion like this, right? Suppose this some particle is moving along a circular motion, right? The speed of this particle is v, but we know that at every point the direction of this particle is changing, right? The velocity is directed in this direction. Here the velocity is along this direction. We can see that the direction of this particle is continuously changing. We can say that it's a case of non-uniform velocity, but we can say that it is a case of uniform speed. Here the speed is not changing, speed is constant. We can say it's a uniform speed, right? But not the case of uniform velocity. It's a case of non-uniform velocity because the direction of the velocity is changing, even though the magnitude of velocity is constant, but the direction of velocity is changing. We can say that it's a case of non-uniform velocity, right? So let's move on to another definition. It's important for us. That's the uniform acceleration, right? Uniform acceleration. So uniform acceleration. So uniform acceleration is nothing. It means a constant acceleration, right? Constant acceleration. By constant acceleration, we mean that neither the direction of acceleration is changing nor the magnitude of acceleration is changing, right? Both should remain constant. Direction of the acceleration as well as the magnitude of the acceleration should remain constant in case of uniform acceleration, right? So in simpler words, if somebody will ask you what is uniform acceleration, you mean to say that acceleration is constant. By constant acceleration, we mean that both magnitude as well as direction of the acceleration is constant, right? If any of these, either magnitude of acceleration or direction of acceleration or both change, then we can say this is a case of non-uniform acceleration, or we can say that acceleration here is not constant, right? So that will be a case of non-uniform acceleration, right? In case of uniform acceleration or non-uniform acceleration, it won't be the case of uniform velocity, because we know when there is acceleration, velocity is going to change, right? If velocity changes, we can say that it's a case of non-uniform velocity, right? So non-uniform acceleration means acceleration changes. Acceleration changes. Acceleration change means either the direction of the acceleration change, right? Or the magnitude of the acceleration change, right? Correct? So uniform acceleration simply means acceleration is constant, and non-uniform acceleration means the acceleration change, either the direction of the acceleration change or the magnitude of the acceleration change, right? Let's try to analyze some of the cases, like how the acceleration affects the speed of this particle, how acceleration change the speed of particle when the uh, speed will be increasing for a particular case and the speed will be decreasing. It depends upon how the speed and acceleration are oriented with each other, right? Let's suppose that we have case one here, right? Case one. Let's suppose we have a particle and it's having the velocity in this direction, right? Correct. And acceleration is also in this direction, right? We take by convention, the convention is that we take positive x-axis of a Cartesian system as positive and the negative x-axis of the Cartesian system as negative. All these conventions will be followed here, right? So we can say that speed is directed here along positive direction, and the acceleration is also directed along the positive direction. So it means that if speed and acceleration are directed along the we can say that if the velocity and acceleration are directed along the same direction, then it's a case where the speed will be increasing. Speed will be increasing. Speed increases, right? Speed increases in this case. So another case is like, suppose that velocity is in this direction, right? It's along the negative direction, right? And the acceleration is also along the negative direction, correct? So once again, since acceleration and velocity are still directed along the negative direction, or they are still parallel to each other, they are still along the same direction. In this case also, even though the speed is directed along the negative direction, right? Acceleration is directed along the negative direction. Or in short, we can say that whenever velocity and acceleration are parallel to each other, right? They are parallel to each other. Whatever be the direction, right? If they are parallel to each other, then in that case, speed is always going to increase, right? Speed is always going to increase. So here, even though the acceleration is directed along the negative direction, but speed still increases, right? Speed increases in this case also, right? So it means that the important condition for the speed to increase is that either the acceleration is parallel to the velocity, or the acceleration is inclined at an angle of theta, which is acute in nature with respect to the velocity, right? Let me try to explore the third case, right? Let's suppose that particle velocity is in this direction, right? Particle velocity is in this direction, but the acceleration of this particle is along this direction, and this acceleration is inclined at an angle of theta, right? It's inclined at an angle of theta, right? Correct. So there will be two components of this acceleration. The one component will be along the velocity, right? It will be nothing. It will be a cos theta, right? And another component of this acceleration is going to be perpendicular to the velocity vector. That will be a sine of theta, right? And this perpendicular component will never change the velocity, or will never change does not change the speed, right? Perpendicular component of the acceleration, the component of acceleration which is perpendicular to the velocity vector, will never change the speed of a particle, right? A sine theta does not change speed of a particle, right? Now, what does this do? The perpendicular component of acceleration only change the direction, right? It will change the direction of particle, right? The direction of particle. So the normal component of acceleration or the perpendicular component of acceleration will not increase the speed of particle. It will not change the speed of particle. It's only going to change the direction of the particle, right? It is only going to change the direction of particle. So in this case, a sine theta is only going to change the direction of the particle. It will not change the speed of this particle. And a cos theta, which is directed along the velocity vector, is the component which will be responsible for changing the speed, or we can say that since this component is parallel to velocity vector, so this is responsible for increasing the speed, right? So in this case also we can say that here theta is acute, right? Theta is acute, correct? And speed increases. Speed increases. Direction is changing, but speed is increasing, right? And let's try to explore one more case. The case is like, let's suppose once again this particle is moving along the same direction, right? V vector, right? Now in this situation here, now this acceleration is not at an angle of does not make an acute angle. Let's suppose that this acceleration vector is making an obtuse angle, right, with the velocity vector, right? Obtuse angle, correct? And let's suppose that this angle is theta here, right? It's theta, and this theta is greater than 90 degree, or we can say it's obtuse, right? If we resolve this if we resolve this acceleration vector into two components, if this is theta, then this is definitely going to be 180 minus theta, right? 180 minus theta. Or we can say that this component of this acceleration will be nothing. It will be a cos 180 minus theta, right? Or we can say that this component here is going to be a sine 180 minus theta, right? A sine 180 minus theta. So the component which is perpendicular to this velocity vector is not going to change the velocity, is not going to change the magnitude of the velocity, right? Or we can say that the component which is perpendicular to this velocity vector will not change the speed of this particle, but it will only change the direction of this particle, right? But the component which is anti-parallel to the velocity vector, which is not parallel to the velocity vector, and this component of acceleration is going to change the speed of this particle, or we can say that since this component of the acceleration is in the opposite direction or anti-parallel to the velocity vector, we can say that this component is going to reduce the speed of this particle, right? This component is going to reduce the speed of this particle. So theta here is obtuse, right? Or we can say speed decreases, right? So acceleration increases the speed of this particle only in two cases. Uh, One case is that acceleration should be parallel to the velocity, or if the acceleration is at an angle of theta with respect to the velocity vector, then the theta angle should be acute, right? Theta should be acute. It means that the theta should be either greater than 0 degree or it should be less than 90 degree, right? Then it's going to increase the speed of that particle, right? And point number two is that the component which is perpendicular to the velocity vector does not change the speed of the velocity vector, or we can say does not change the magnitude of the velocity vector. It only changes the direction of the particle, right? So the component which is perpendicular will never change the speed. It will only change the direction, right? So normal components are always responsible for changing the direction of a particle, right? Point number three is that the speed will only decrease for the particle if the angle between the acceleration vector and the velocity vector is obtuse. It means that it should be greater than 90 and less than 180 degree. In that case, the speed of this particle is always going to decrease, because there will be a component of acceleration will be which will be opposite or anti-parallel to the velocity vector, which will decrease the speed of this particle, right? Or we can say that if the acceleration or if the acceleration and velocity vector are anti-parallel, right, like this, if the acceleration and the velocity vector are antiparallel to each other, then in that case also, the velocity speed is going to decrease. Speed decreases, right? Speed decreases. Or in that case also, suppose that this velocity vector is in this direction, right? And now acceleration along this direction. In this case also, because they're once again anti-parallel to each other, the speed is going to decrease, right? This acceleration is going to decrease the speed of this particle, and in this case also the acceleration is going to decrease the speed of this particle. So speed of the particle will decrease in two cases. One case is that the acceleration is completely anti-parallel to the velocity vector. In the second case, if the acceleration is making an angle of obtuse, right? Obtuse angle with the velocity vector, right? It means that theta is greater than 90 and less than 180 degree with the velocity vector. Then in that case, there will be always a component of acceleration which will be anti-parallel to the velocity vector, and that component is going to decrease the speed of particle, right? So in this case also, the speed of this particle is going to decrease, right? Speed decreases. So that was it with respect to how acceleration and velocity vector are related, how acceleration change the speed, whether it decrease the speed, whether it increase the speed, or whether it only changes the direction of the velocity, right? If suppose that the velocity is along this direction, right? Velocity is along this direction, and the acceleration is completely normal, or perpendicular to the velocity vector, right? Then speed is constant. Speed does not change. Speed remains constant. Only direction changes. Only direction changes. So this acceleration will be responsible for the changing the direction. So only direction changes. So the velocity will change because the direction will change, right? So this was about how the acceleration how acceleration affects the velocity of a particle at different angles, right? So we conclude with that if acceleration is parallel to the velocity, right, it's going to increase the speed of that particle. If the acceleration is anti-parallel, it's going to decrease the speed of particle, right? So let's try to move on to the next concept, that's trajectory of motion based on acceleration. So acceleration once again play a very key or important role in deciding the trajectory of a particle, right? How the trajectory is going. We also studied that acceleration can change both direction as well as speed of that particle. So if acceleration change the direction of a particle, can change the direction of the particle, then it means that acceleration has got to play a role in deciding the trajectory of a particle, right? So let's suppose acceleration can be of two types. One is constant acceleration and another is non-uniform, right? The acceleration which is not constant, non-uniform, or we can say variable, right? Correct. We can say variable acceleration, right? Uniform, A is constant or A is variable, right? Correct. And now if the acceleration is constant, right? If the acceleration is constant, now there will be two cases, right? There will be two cases. Suppose initial velocity vector is zero, right? U is zero, correct? U is zero at time t equal to zero, correct? Or if there is a U initial velocity, then if U vector is parallel to A vector, right? Two cases. Acceleration is constant. In that case, if U vector initial velocity is zero at time t equal to zero, or if there is some initial velocity, but initial velocity vector is parallel to the acceleration, then in that case, the particle is always going to move in a straight line path, right? The particle moves in, body moves along a straight line. Along a straight line. And the next case is that acceleration is constant once again, but A and V, A and U are at an angle theta, then the trajectory is going to be a parabola, right? Trajectory will always be parabola. Trajectory will be parabola, right? And the third case is that if the acceleration is non-uniform or variable, in this case, the particle can follow any path. It depends upon how the acceleration varies with the time. For different variation of the acceleration with time, the path of the particle will be different. So it depends upon the acceleration, how acceleration varies. So it can have any path, right? It can have any path, right? So the case is like that. Let's suppose that the body was initially at rest, so u is equal to 0, right? And suddenly what is going is that we apply some force or we accelerate this body, then this body is always going to follow the direction of the acceleration, or this body is always going to follow a straight line path, right? It will follow a straight line path, correct? And the case second is that suppose that this body was having some initial velocity vector, right? Let's suppose the initial velocity vector is along the x direction, right? And we are also applying a force and the acceleration is also along the x direction. In this case also the body is going to continue to move along the x direction, or we can say that in this case also the path of this particle is going to be a straight line path, right? So it's a straight line path, right? So the third case will be, let's suppose that acceleration is constant, but in this case this is the velocity, right? Acceleration is constant, but in this case the acceleration is not collinear or parallel to the velocity vector, right? This acceleration is at an angle of theta, right? With the velocity vector, right? Then what this acceleration is going to do is that it will change the direction as well as the magnitude of the speed of this particle, and particle will always try to bend towards this acceleration, right? Particle will always try to bend towards this acceleration like this, and it will be following a parabolic path. Which path? Parabolic. Let's suppose that the acceleration is like this and the velocity is like this. So this is our u vector and this is our a vector. Then path of this particle is going to be like this. It's once again a parabola. Correct? So let's if suppose the acceleration is directed along this and the velocity vector is along this direction, then this particle is going to follow a parabolic path like this. So once again this path will be a parabola. It will be parabola only if acceleration is constant, right? The acceleration should not change the direction and the magnitude also, right? So that's it. We studied how the acceleration plays an important role in deciding the trajectory of the particle, right? So now in this section, we'll be discussing about the different equations of motion, right? And particularly, we study the equations of motion We study the equations of motion only when the acceleration of a particle or system is constant, right? We can say that equations of motion under constant acceleration. Under constant acceleration. So equations of motion under constant acceleration. So we know that our P is nothing, it's defined as dx over dt, right? Where x is nothing, it's a position vector, right? And we also know that if we have to calculate the displacement, or if we have to calculate the position vector, right, for the displacement. So what we can do is that we can just integrate this velocity vector with respect to time. Integrating velocity vector with respect to time will be getting the displacement vector, right? Or the second case, we define acceleration as dv over dt, correct? Or the acceleration can also be defined as second derivative of the position vector, right? Or we also define this acceleration as v dv over dx, right? So this is how we define the accelerations, different equation of acceleration and velocity as well. So the important point for all these equations is that these equations are valid everywhere, right? Everywhere in the sense, even if the acceleration is constant or the constant acceleration is variable, right? They're still valid, right? But when we'll be studying the equation of motion, we'll be studying all these equations only under a single condition. The condition is that acceleration should remain constant, right? If the acceleration of the system is not constant, then we cannot use all those equations, right? So we'll be deriving all these equations with the condition that we assume that acceleration of the system is constant, right? So our A, we can use this equation A is dv over dt, right? Then we can see integral of A dt, that will be equal to dv, right? Let's suppose at time t equal to 0, the velocity was v was equal to u, that's initial velocity, so it will be u to v, and we have assumed that a is constant, right? A does not change, a is a constant, right? uh, from time t equal to 0, velocity was u, and time t equal to t, there is some final velocity v. So a will come out of the integral, so it will be integral of dt from 0 to t, right? So it will be integral of dv, right? So it will be nothing, it will be integral of dv will be v, that's u to v. So we'll be left with here at, so it's nothing, upper limit minus lower limit, so v minus u, or we can conclude that v is nothing, it's u plus at, right? U plus at. So v is equal to u plus at. We can write it in vector form that v vector is equal to u vector plus a vector t, right? So this is our first equation of motion, right? This is our first equation of motion. So this is the first equation of motion. That's nothing. That's v is equal to u plus at, right? We know acceleration is nothing. It's equal to, just a minute. Our acceleration is equal to dv over dt, right? dv over dt, correct? Our acceleration is nothing. That's equal to dv over dt, right? Or you can say that our velocity is nothing. Our acceleration is nothing, we can write it as also our acceleration is equal to p dv over dx, right? P dv over dx, correct? Let's integrate this. So it will be a dx, that will be equal to v dv, right? Now if we integrate it, let's suppose initial position vector was xi and the final position vector was x final, and initial velocity was u and the final velocity is u, right? So integration a will be out of integral, will be left with a dx with the limits xi, that's the initial position vector to the final position vector. Integration of v dv will be v square with the limits u to v, right? So from here, integration of dx will be x, dx will be x, right? So it will be ax with the limit initial position vector to the final position vector. So we'll be left with v square minus u square, right? V square minus u square. So from here we'll be left with a x final minus x initial, right? Sorry, it will be v square over 2 here. It will be v square over 2, correct? It will be v square over 2. So integration of v dv will be v square over 2, right? We'll be having 2 here, factor of 2 here. So it will be v square minus u square over 2. So from here, our v square is nothing, that's equal to u square plus 2a x final position vector minus x initial position vector. We know that displacement vector is nothing, that's equal to final position vector minus initial position vector, right? We can write it as s. So v square will be nothing, that will be equal to u square plus 2as, right? So s is the displacement here. So this is our second equation, right? This is our second equation for the motion when the acceleration is constant, right? When the acceleration is constant. We can derive the third equation as well. Let's suppose that we know that velocity is nothing, it's defined as v dx upon that's dx upon dt, right? So we can write it as v dt, that's equal to dx. Integrating it, let's suppose initial position vector was xi and the final position vector is x final, and let's suppose the initial velocity was u and final velocity is equal to v, right? Final velocity is equal to v, correct? Because sorry, we have to calculate the limits with respect to time, right? So at time t equal to 0, velocity position was xi, and at time t equal to t, the position is x final, right? So we know we can replace this v as u plus at also, right? A plus at, we're integrated it with respect to time, so it will be nothing, integration of x with respect to x will be x, so it will be x final minus x initial, and we can write it as displacement, right? That's the final position vector minus initial position vector, right? So integrating it, it will be nothing, it will be ut plus half at square, right? That's equal to s. Or we can say that s is nothing, that's equal to ut plus half at square, where s is nothing, it's a displacement, right? It's a displacement. Or we can rewrite it as, if we have to find the final position vector, so final position vector will be nothing, it will be x final, that will be equal to x initial position vector plus ut plus half at square. So these are the three important equations of motion, right? Three important equations of motion. We can write this equation of motion in this form also, because it's also a very important form, right? So summarizing all these equations of motion, we can write here all these equations. The first equation we calculated was that v is equal to u plus at, right? And the second equation we calculated was v square is equal to u square plus 2as, or we can also calculate say it like this, it's v vector dot v vector plus that's equal to u vector dot u vector plus 2a dot s, right? So the third equation was nothing, that was s is equal to s vector that's equal to ut plus half at square, right? Half at square, right? Ut plus half at square, or we can rewrite it as x final that's equal to x initial plus ut plus half at square, right? So these are the equations of motion, very important equations, right? These are the equations of motion, very important equations, right? So we can use all these equations whenever these are case of constant acceleration. We can use all these equations, right? We can use all these equations whenever we have a case of uniform acceleration, right? So that's it for today. In the next class, we'll be discussing about the motion under gravity, and we'll be rewriting all these equations whenever the particle moves in a gravitational force or motion under gravity, right? So that's it for today. Take care and goodbye.